Hi everyone, my name is Ivana. I'm from the Vienna University of Technology, and today I would like to talk to you about automated game-theoretic security analysis of blockchain protocols. I know it's quite a long title. There is game theory, there is automation, there is security, and there is also blockchain protocols. But no need to make sense of it as a whole right now, because we're going to go through each of the parts together during this talk. Starting by something that most of you might be familiar with, which is blockchains and their protocols. So basically, we have blockchains, which are just chains of blocks. The blocks store some data, and then they're all linked in their chronological chain. They provide us cryptocurrencies and allow us to track the balances. And in this manner, they enable decentralized finance, such as auctions, crowdfunding, and so on. How the blockchain operates is described via protocols, which are basically sets of rules. And these protocols rely on punishment mechanisms, which makes them a very popular target for attacks. And since we have the possibility of attacks, what we want to ensure is that we have security analysis of blockchain protocols. Now, security of blockchain protocols itself is a very wide and broad term, depending on the aspect from which we're looking. First of all, we have the implementation aspect. And in this context, we might ask ourselves, if I have a password and I enter it somewhere, what happens with it? So is it just used to log me in to the system? Or is it also stored somewhere where I do not want it to be stored? Another aspect that we could have is the cryptographic security. And in this context, we could ask ourselves, if I have a key, can a malicious person steal this key? Last but not least, we have also the aspect that deals with the economic incentives that drive user behavior. And in this particular setting, we could ask ourselves, if I have a password, would I like to share this password with someone, even though I might not be supposed to do so, just to win something more for me, or maybe cause someone else some loss. And depending on which aspect we are considering, we either talk about implementation security when it comes to the implementation, or we talk about cryptographic security when we are concerned about the cryptographic concepts, or in the very third setting, we talk about game-theoretic security when we want to analyze the economic incentives that drive user behavior. In our work and in today's talk, we will focus on the game-theoretic security. So as I said, we have security analysis of blockchain protocols, and now we focus on the game-theoretic aspect of it. Okay, so how is this done? As I mentioned previously, we have our blockchain protocols, and what we want to do is we want to translate them into game-theoretic models. And once we have our game-theoretic models, we want to perform the security analysis. And as you might have guessed, we want to do this automatically. So there are papers on this slide that correspond to each of the parts of this whole approach. In case you want to look them up, I promise to give you a list of the papers at the end of the talk. Okay, and for the rest of the talk, I would like to focus on each of these parts individually, starting with the game-theoretic models. So how do our game-theoretic models look like? Well, here is one example. Please do not look at the tree yet. We're going to go through it together. So for those of you familiar with game theory, we have extensive form games. And for those of you not so familiar with game theory, or also familiar, but as a revision, we have finite trees. So this is very important that we have finite trees. And one such example is depicted on this slide. This particular example is a very simplified version of the closing phase of the Bitcoin Lightning Network, in case you're familiar with it. And in this setting, we have particularly two parties, A and B, that have a channel between them. And in this part of the protocol, we're talking about closing. So one of these parties wants to close the channel, and we will now see how it is translated into a game-theoretical model. So first and foremost, we have our players, A and B, and the players can take actions. At the very beginning, A can either choose to take action CH, which means that they choose to close the channel collaboratively and honestly, after which B can either ignore this proposal or sign it. Another option that A could take is to close the channel unilaterally and honestly. Or, last but not least, A can try to be dishonest, after which B can either ignore A or try to prove by taking action B that A was dishonest. As you can see at the leaves of the tree, we find the utilities, which are terms of real, and it is important to mention that we use symbolic variables. A concept that will be important later when we talk about the security concepts is the concept of joint strategy, which is basically going through each node of the tree and picking one of the available actions at that node. Last but not least, we always have an honest behavior or an intended scenario, which is fixed. So in this particular example, it would be for A to close collaboratively and honestly, and then for B to sign this closing, so basically the red arrows. And we always analyze the protocol with respect to one honest behavior or intended scenario. There might be protocols where there are multiple allowed behaviors, and in this case, we always fix one intended behavior at a time and then analyze the game for each of them separately. As I mentioned previously, this is a very, very simplified version of the closing phase. And in case you're interested how the real closing phase or closing game looks like, it looks like this. And as you can see, it's quite a large tree. And in this tree, we even have some subtrees like S1, S2, S3, S4, which are again trees themselves, but we do not depict them on this picture because they didn't fit. So basically, this is S1, this is S2, S3, S4, and so on. And as you can already see, this is already a very large tree with trillions of joint strategies. And it's really interesting because this is one of the smallest real-world examples. If you take other protocols, they're much larger and they have even more joint strategies. Okay, so we've seen how our game theoretical models look like, and now we might ask ourselves, what do we want to do with them? What do we want to ensure, and how do we want to analyze these protocols? Well, for our security properties, we differentiate between three types of behavior. The first type of behavior is the honest behavior or the honest users. They always follow the protocol, they always follow the rules, no matter what. Another type of behavior that we consider is the rational behavior. The rational players might deviate from the intended scenario if they're incentivized to do so. That is, if a deviation from the intended behavior promises them a strictly larger utility. Last but not least, we also have the Byzantine players. They're malicious, they can deviate at any point, they potentially want to harm other players. Keeping in mind these three types of behaviors that user can have, we want to ensure that two properties hold. The first one being incentive compatibility, meaning that the honest behavior is always rational. And the second property is Byzantine fault tolerance, meaning that the honest players are never harmed. So basically, with these two properties, with the first one, we want to ensure that the honest and the rational players are the same set, and then we want to protect them from the Byzantine players with the second property. We define a protocol to be game theoretically secure if and only if the honest behavior satisfies these two properties. Now, since we know how our properties look like and when can we claim that a protocol or a game is secure, let us revisit our closing game. And applying the definition of a secure game, we ask ourselves, is the honest behavior incentive compatible and Byzantine fault tolerant? Well, there is a bit of a trick here. We cannot really check whether the honest behavior satisfies these properties. This is why we use the notion of a joint strategy that I told you previously. So basically, with this notion of a joint strategy, we want to find one strategy. So basically, at every node at the tree, fix one action, such that if a player takes this strategy, which is claimed to be secure, and they play or act according to it, they're safe no matter how the others behave. Additionally, we want to enforce that this joint strategy is an honest one, meaning that whenever we are along the honest behavior, the honest action is taken. Okay, and let us recall about the closing game that we had trillions of joint strategies, right? So finding one or checking whether there is one which satisfies these properties, if we do this manually, as this person that is terrified on the slide, this is very tedious. This takes days, if not weeks, error-prone, and last but not least, boring. Which is why we want to do this in an automated way. So here is a pipeline about how we do this automatically. This is a very high-level abstracted view of how it was done, and this is basically the first implementation, so the prototype, so to say. What we do is we take our game, any initial constraints that might hold for the symbolic variables. We take the honest behavior and the security property that we want to analyze, and we translate all of this into a large set of SMT constraints. We send this set of SMT constraints to the SMT solver, and then we inspect the output of the SMT solver. Depending on the output, we can either claim that a protocol is secure, in which case we can perform strategy extraction, so we have this one strategy according to which players can act and be safe. And if a protocol is not secure, we can either do precondition generation or counterexample generation. The preconditions are basically the weakest preconditions that need to hold for the protocol to be secure, and the counterexamples correspond to concrete attack vectors. This approach is sound and complete and has been automated in the tool which is called Checkmate. Now let us revisit the closing game once again. Using this very first implementation or prototype of Checkmate, we needed 30 seconds execution time to check whether these properties hold or not. And after that, we came up with a slightly smarter version of the tool, which was Checkmate 1, which cut down the execution time for 30 seconds to 0.3 seconds. And if you think this improvement was cool, stay tuned for what's coming next, because in my opinion, it's even cooler. Well, this worked well for protocols of smaller or medium sizes, but we still had significant scalability issues for protocols of larger size. And as I already mentioned, the closing game belongs to the ones that are smaller in terms of real-world protocols. So for the larger protocols, we decided to implement some compositionality techniques. And our approach currently employs two levels of compositional reasoning, the first one being stratifying over the players. So let us recall, we have our model and we want to analyze it for our players Alice, Bob, and Eve. And what we did previously was to basically analyze the whole model for all the players at once. In our compositionality project, we proved that this is indeed equivalent to showing that the protocol is secure for Alice. And if yes, we continue the analysis and check whether it's also secure for Bob. And if yes, then whether it's also secure for Eve, each time assuming that the fixed player is honest. Every time that we analyze a protocol for one fixed player, we perform a reasoning on the second level, which we call divide and conquer subtrees. And this is actually analyzing only the relevant subtrees and not all the possible ones. How does this look in more detail? Well, let's say we have our model and we want to analyze it for Alice. And what we do is basically we determine which parts of the protocol are relevant for Alice. And we only do these subtrees, and determining which subtrees are relevant for a certain player depends on certain rules, which I'm not going to discuss in detail due to time constraints, but you are welcome to ask me if you're interested after the talk. And once we have the relevant subtrees, we just analyze the subtrees and combine the results either conjunctively or disjunctively, also depending on some rules that I am not going to discuss. As you might imagine, we do not do this just one time. We're also doing this in depth. So once we have the relevant subtrees, we also take the relevant subtrees of the relevant subtrees, and we go as deep down as to the leaves, where we have the utilities. We also analyze the leaves, combine the results, and propagate everything upwards to the top level. So this two levels of compositional approach gave us a really nice improvement, but also they gave us another feature which we call piecewise analysis. The problem that we had with really, really large protocols was that some of them were not even able to be generated, let alone analyzed. We had protocols with over 144 millions of nodes, which exceeded also our allocated disk space, and we're not able to generate them, let alone analyze them. What we currently do with such protocols is we detect some subtrees within this protocol. So this can be a phase that we know of, a subpart of the protocol, or basically any random part of the protocol where we want to cut it. We take one such subpart or subgame. We analyze this as a standalone game, so we send this to Checkmate, and Checkmate gives us the security result of the subgame. Once we have this, we can plug this in the supergame, and we can basically repeat this as often as we want. Once we have the security results of the subgames, we can just keep the security results and discard the subgames themselves. And as you can imagine, the security result of a subgame is much smaller than the subgame itself, which is why we do not exceed the disk space when generating the protocols anymore. So we end up with a supergame where some results are already pre-computed, and the supergame is much smaller. So now we can send the supergame to Checkmate, and we obtain the security result of the supergame. We automated the compositionality approach in a version of the tool called Checkmate 2.0, and I would very briefly like to highlight some of the results of the experimental evaluation. So for tic-tac-toe, the old tool did not terminate within 8 hours, whereas the new tool terminates within 42 seconds. In terms of SMT calls, the old tool had performed one SMT call because it captured the whole tree and the aspect of all players at once, whereas the new tool has over 10,000 SMT calls, but each query is super small, super simple, and does not impose a burden to the solver. So even though we have 10,000 SMT calls, we're much faster. In terms of evaluated nodes, the old tool analyzes all of the nodes as expected, whereas the new version of the tool analyzes significantly less nodes. Another interesting benchmark is the routing protocol, which some of you might be familiar with. And for the routing protocol, the old version needs about 50 minutes for old counterexamples, whereas with the new version, we do this within 5 minutes, also employing compositionality techniques for the strategies and the counterexamples. Last but not least, one aspect I did not talk about is the modeling. I know I'm probably already running out of time, so we just skip through this part. In case you're interested and you want to know how we translate the protocols into game-theoretic models, you can look up our IFM paper. There we talk about some modeling principles that need to be considered in order to come up with a faithful game-theoretical model. And also, these modeling principles provide us a stepwise instructions on how we can do this translation. Most importantly, we have a template in DSL which is ready to be used. Here's also a glimpse of all the benchmarks that we have so far, going from small to examples to medium-sized games, going to also real-world models, and the number of nodes and time that we need for the analysis. In case you're interested in the time that we need for strategies, counterexamples, and weakest preconditions, this can be looked up in our UPSLA paper from this year. And with that being said, I am already at the end of my talk. Thank you for your attention. Here is the list of papers in case you want to look something up, and also a QR code of the repository in case you want to use Checkmate. And I'm looking forward to any questions or comments that you might have. Talk to me today or also write us an email. Thank you.
Thank you very much. Very impressive slides.
Thank you.
And content too.
Thank you.
So any questions? Yes, Stefan.
A technical question. So you have two properties that you're interested in, right? This that the set of honest behaviors agrees with the set of rational behaviors, and then that you get Byzantine fault tolerance. So in particular for the first one, I'm wondering what features of SMT you need. Can you encode everything in quantifier-free formulas, or?
So
it looks to me like you're reasoning about sets, and you would need a lot of quantifiers there.
Yes, so this was actually the benefits of the compositional approach. We removed the quantifiers because with the compositional, previously we did have quantifiers which made everything way more complex, but now with the compositional approach we do the heavy lifting in the code, the reasoning with this all like rules depending on certain conditions that we verify, and we just call the solver within the leaves. And at the leaves we have no quantifiers except this implicit universal quantification because of the symbolic variables.
So I'm actually wondering, like for tic-tac-toe, which is supposedly a very simple game, right?
Yes.
What does it actually mean to do all of this analysis for tic-tac-toe? Because in some sense, analyzing standard tic-tac-toe has been done for ages, and it's not taking 50 minutes usually, right? So what does it actually mean?
Yeah, so this is a very good point, and tic-tac-toe is also not a blockchain protocol, right? This was explicitly, and as you can see, we have 500,000 nodes. So this was specifically done, modeled in a very inefficient way because we wanted to have a large benchmark. And we came up with tic-tac-toe before we had other benchmarks as the one with 144 millions that I talked about. So this is specifically modeled in a very inefficient way. If you model tic-tac-toe more efficiently with symmetry breaking, it would be around 50,000 nodes.
Yeah, but let's say even without symmetry breaking, like there are like what, 3 to the 9 states or something like that, or even less.
But you have to think like if we have the first player has 9 options, right? And then at every point we have to consider all the possible, so there is a blow up in terms of the size of the tree.
Except like some things you can reach in 2 ways, right?
Yeah, that's what I mean, tic-tac-toe is extremely inappropriate for CSP and FDR, but nevertheless I found a way of doing it and it solved it instantly.
Happy to chat about that.
I mean,
Yes, there's another question back there.
So when you describe checkmate, it looked like what you're analyzing are really just game trees, but this could apply for any two-player interaction situation, not necessarily games where honesty and rationality that you described in the first part are necessary. So are you using that to prune your game trees in some way, or?
So yes, we have rules. So basically in this compositionality approach, we have ways of pruning the trees. And this is expressed through the second level of reasoning, where we have the dividing and conquer of the subtrees at a certain point. So let's say here at A, we have certain rules to determine that maybe this subtree is relevant, and the second one as well, but the third and the fourth are not. So depending on certain rules, like for example, which player is currently having a turn, is this the player that we're checking the property for, are we along the honest history or not, depending on which conditions are satisfied, we only analyze some subtrees and not all. This is kind of the pruning that we perform.
Do you lose anything with this compositional approach?
Sorry?
Do you lose anything by doing this? Like, do you over-approximate or, that kind of stuff anywhere?
We're still sound and complete. And in terms of experimental evaluation, we are almost always better. There are, of course, some benchmarks where the compositional approach underperforms, but this is due to different reasons. It's mostly the structure of the benchmark itself.
Another question? A quick one?
Yeah, a very maybe naive question, but couldn't we have some sharing in the trees? So not trees anymore, but tags.
Yes, so this could be also something that we might consider in the future. Currently, we only have trees, and they're finite trees. So in case we want to duplicate a subtree, then we would need to have it 2 times. But using this piecewise analysis, you can recognize it as a subtree, you can analyze it just one, and plug in the result at both places.
All right. Well, I think it's time for the break, but thank you very much again.
Thank you.